Hey everyone, it's Mr. Hoop back at it with some more Algebra 2. Today we're talking about the LCD or least common denominator of rational expressions. But first, before we talk about that, we got to talk a little bit about least common multiples first, which will help us get those least common denominators. So to find the least common multiple of polynomials, okay, first you're going to want to factor, okay, each of your polynomials into its prime factors. So separate them all out until you can't take out any more factors. Then you're definitely going to want to list all your factors, okay, in each of those factorizations, right? Then we have to use the greatest number, okay, of factors per each LCM, okay, per each factorization in your LCM, sorry. And finally, you just multiply them all back together and you'll get your LCM right there, your least common multiple. So let's do a couple examples because those steps kind of don't mean a whole lot without the examples, right? So let's take a look. Here's my example number one. I have three different polynomials, okay? They're polynomials because they're using the variables there with varying degrees. Okay. So if I were to write out 2a cubed as a list of factors, I have 2, right? That's my number. And then I have a 3 times. Okay, so I have 3 a's in my first term. Right? This is all multiplied together, just in case you were wondering. In the second one, I've got 6. Well, 6 isn't prime, so let's split that up. This is 2 and 3. 2 times 3. All right, pretty easy, simple factorization. And then I have 4 a's this time, as well as 2 b's to tack on to my list. So let me go ahead and do the final one here. My 4a cubed b5. 4 is not prime either. It's 2 times 2, right? Then I've got A, another 3 a's there on that one, and then b 5 times. Okay, so let me split these up so we can talk about them in quick detail. Okay, so I'm done with my step 2. I'm done with my step 1. Okay, now I just need to think about what's the highest number per each group in each, for each of the factors, sorry. Okay, I'm going to use a different color for this one. When I'm talking about the factor of 2, the highest number of factors per any of these groups is the last group. There are 2 of them, so I'm going to put 2 squared here. 2 2's. Then I have to consider 3. That's there as well, so here's my 3. And then as for the a's, I have 4 a's in the middle, 3 on the left, and 3 on the right. Well, 4 is the greatest number, so I'll be multiplying by a to the fourth. And b's, well, the highest number of b's is definitely that b to the fifth on the left, on the right, sorry. So these are all my factors of the greatest amount per each of these. And so all I have to do is string them all together, make it nice and pretty. In the end, I'll be left with 4, that's 2 times 2, times 3. Okay, so that is 12. Go ahead and erase that and replace it with 12. Got a little ahead of myself there. So I got 12, that's 2 squared times 3. A to the fourth, because you can't really do that, and b to the fifth. So this is my least common multiple in the first example. Okay? And what that really means is that's where they overlap. If you were to take out a nice multiple times table, you would keep multiplying it by, 2, 3, 4, whatever factors, okay? But this is the factor, this is the number where those numbers will match. Those numbers share this multiple. Let's go ahead and do this next one as well. And I'll save the other stuff for later. Okay. Perhaps try it on your own if you want to give it a shot. But you've got 5x squared y and 25x cubed y5z. So that's a lot in the second term. Let's figure out this first one first. 5 is by itself, and then I've got x twice, and then I got y once. So there's my first one. Then over here, I've got 5 squared, right? 5 times 5, that's my 25. 3 x's, 5 y's, and looks like 1 z. So I got a pretty varied group of variables there. Again, I'm going to split them apart because they're technically 2 different factors, 2 different numbers I'm considering. And then I just got to figure out what's the greatest number. Okay. Greatest number in the second one here is 2 5s. So that's what I'm going to be using. So 5 squared, That's 2 factors of 5. Then again, I have x, 3 of them over here, so that's going to be x cubed. Okay. I got 5 y's here and 1 y there, so I think that's pretty obvious which one's bigger. And then 1z and no z, so we do have at least 1z. Simplify it all out. 5 times 5 is 25. X cubed, y to the 5th, z. Now, you might notice that this is actually just the same as this guy, the second one. Well, that's because all the greatest numbers fell on the right one. Okay. So sometimes when you take out these least common multiples, your multiple will end up being one of your factors there, one of your polynomials. It just so happened with this one that was the case. All right, let's go ahead and clear our board. You can pause, obviously, to look at it and continue on with another example. So I'll be doing this one on the left here, and then we'll just let you guys, I'm sorry, I'm going to do the one on the right, and then I'll let you guys think about those other ones. Okay, we'll do them in class if you need to. In this one on the left, or on the one on the right, we have x minus 7, and x plus 1. Now, when you do the factoring for this, x doesn't have anything multiplied by it, so we just leave it there. X minus 7. Do we know of any factors of x minus 7? Well, we definitely know that there's a 1 in x minus 7. That is definitely a factorization of it. But can I actually factor x minus 7 at all? Well, no, we cannot, because it is a simple binomial with just an x and a constant. So, of course, we're not going to have any other factors. Likewise, that one on the right doesn't have any factors either. It's just itself. So when you're working with these kind of binomials and trinomials and stuff like that, they count as their own factor. But unless you can factor them with a method you know, such as difference of squares or ACB tree, they don't have any other factors to go into. They are prime, as we saw. So now we just need to figure out what's our highest count of each factor. Okay. Now this is maybe where some people might get a little lost. Okay. But each of these factors are different. Okay. Each of these factors are different. Since they're all different and they're only going to be 1 each in each of them, you just multiply these all together. X minus 7, and x plus 1. And this is our least common multiple. Okay, I'm not going to ask you to multiply it all out. Usually it's better to work with it in the factored form anyway, so there doesn't really serve a purpose to simplify it all out. So just to kind of reiterate, terms, okay, if you have terms you cannot factor, then it's the prime already. You cannot factor it any further, it's done. X itself is already prime, as we all know. Or rather, can't be factored into any numbers without knowing what x is, but we don't, so we're just going to assume it's prime. All right. The rest of these problems I'm going to leave for you. Okay. They kind of have some overlapping factors, so if you take a look at those in the class, we'll talk about that then. All right, so on to the next topic then. So this is the part where we're going to talk about some least common denominator. All right, so the entire point of the least common denominator technique is so you can rename your fractions, your fractional functions, so that you can work with them a little easier. Okay, so first of all, we need to find the least common multiple. That was the entire point of the first section of the denominator, right? So we'll get to the examples in a sec, but we're going to multiply both the numerator and the denominator by a common factor to obtain the least common denominator. Okay, so we'll explain a little more about what that means in a sec. And finally, if you get a chance, you can simplify if necessary. Okay, we probably won't use this step too much as long as we kind of hit it right on the head. So first example, 5 over 2x squared. And I'm trying to get it to be this whatever over 8x cubed y. Okay, so again, take a look at our denominators. We want to find our least common multiple. Let's factor it out. 2x squared has a factor of 2, has a factor of x, has a second factor of x. So that's 3 factors in total. This other one has 8, so that's 2 times 2 times 2. That's 2 cubed, actually. And then I have an x 3 times, because it's cubed there, and then y once. And again, splitting them up so you can figure out which group has the biggest number of factors. It looks to me like 2's. I'm going to be using 2 cubed for this one because there's 3 on the right and 1 on the left. For x's, I'm looking to look at the x cubed right on the right as well. Okay. And finally, y, there's only one y and it's on the right, so this is our least common multiple. which is actually the same as this guy again. So we're going to be using him as well. Now we get to step 2. Step 2 is a little more difficult. Step 2 is a little more difficult. What do I mean by multiply the numerator and denominator by common factors to obtain the least common denominator? What is Mr. Who talking about? Well, I'm talking about the first function on the left. I'm talking about this guy. I'll use a different color here. This guy on the left. I'm talking about multiplying that one by some factor to obtain the least common number. Now, if you notice, okay, in the least common multiple step, I did ignore the left side. That is true. However, okay, all I need to do is multiply by enough factors to get up to this least multiple, okay, this least common multiple. I already have 1, 2 in the left, so I only need 2 additional 2's being multiplied in order to make up to that 8. So what am I multiplying by? I'm multiplying by 2 squared. Okay, this is that one single 2, right? Times 2 squared, and that's my 2's, times x squared, that's what I started with, right, in the denominator, times how many more to make up to the 3? Just 1. And finally, I don't have any y, so I do have to add that extra y. So let me underline here, in case you got lost. The first 2 comes from our 2 on the left. Our x squared comes from our 2x's on the left. Where this next one, I'll use green here, these guys are what we need in order to make up our least common multiple, the green. All right, so these green guys are actually what we need to multiply the top, the numerator, by in order to get our final answer. So when we take these, it's 2 squared x and y. So I'm going to take my, go change back to black here. I'll take my 5 out here and multiply it by 2 squared x and y. And what you'll end up with after you do that multiplication, 5 times 4, that's 20. And then I've got x, y. So this is what goes in the blank right here. Whew. Okay, so there's a lot of math there, a lot of mental exercises there. In the end, I'm going to give you another strategy. Okay, so I'll do that strategy with this next example. Okay, so for the second example, number 2, I'm going to show you another method to do this that involves a little less mental hurdle and more computational math. So depending on which one you prefer, you could definitely choose whatever one. So first things first, I need to find out my common multiple. Okay, so I need to find out my common multiple. That would be, here's 3a cubed, b squared, and c. Here's 9a5, b squared, c4. Okay. Now, when I figure out what the factors are, 9 is actually just 3 squared right here. There's 2 3's in there. And then I got 3, 2, 1, 5, 2, 4. So when I take a look at which has the higher number, I think I'm settling on 9. That's 3 squared. A to the 5th, that's because 5 is bigger than 3. B squared, they're the same, so that's okay. And C to the 4th as my common multiple. This is my common multiple. Okay. So I'm going to go keep working over here with this little empty space I have. Okay. What you can do is you can take the 2 over 3a cubed, b squared, and c, and you can just multiply both sides by the least common multiple. Okay. So as I write that out, there we go. Okay. Now, if you do this, you'll end up with something very unwieldy looking. 2 times 9 is 18, a cubed, b squared, c to the 4th. Okay, cool. And down here we have 9a5, b squared, c4. Times the 3, sorry. So I actually have to erase that and put in a couple extra numbers. So, sorry about that. We've got 27, a to the 8th, b to the 4th, c to the 5th. So it's quite a bit more than what we're used to. Okay. Now remember, we want the least common denominator. Least common denominator. So what that means is I'm actually looking for this, okay? Looking for this denominator. How do I get here? How do I get there from here? I actually just take my previous denominator, my 3a cubed b squared c, and just divide both sides by it. So I'm going to divide by 3a cubed b squared c. Divide 3a cubed b squared c. So, like I said, this is a little more computationally intense. It is still a valid method should you choose not to think about what do I need to multiply up. Essentially, it's the same process, okay, but it's a different way of doing it. So let me just divide my top here. 18 divided by 3. That has to be 6, right? A to the 5th divided by a to the 3rd. 5 minus 3 is 2, so I have 2 more a's left. B squared divided by b squared. Well, I don't have anything anymore. C to the 4th divided by c. That's c4 minus c1. Okay, that's 3. And then when you divide the bottom, you should end up with the thing we were actually looking for. 9a to the 5th, b squared, c to the 4th. And so this becomes our fully simplified, okay, our fully simplified end result there. So that blank right in here is going to turn into that 6a squared c cubed. Okay. Pretty difficult with just these factors. Let's do a couple with binomials and see where we are here. Clear all the drawings out. Okay. So with the binomial here, I'm talking about number 3 now. Okay. I've got 2 over x plus 4 equals something over x squared minus 16. Now, if you factor both of these pieces, you'll find that x plus 4 is its own factor. It doesn't factor. And then the other factor is x plus 4, x minus 4. Okay. So those are my factors for the x squared minus 6. Difference of squares. So just remember that. Then I need to find out, well, okay, I have a factor of x plus 4. So here's my LCM part. That's the same for both of them. And then I have one factor of x minus 4 just in the right. The other one doesn't have it. So this right here is my LCM. All right. Now with that knowledge, I need to find out how to get the numerator and denominator on the left to match this with a denominator like this. This is actually fairly simple, right? If you think about it, 2 over x plus 4, well, it already has x plus 4 in the denominator. So all I have to do is multiply 3 by this to match the denominator on the right side of the equation. So 2 times x minus 4 would equal, okay, what's at the top for this, sorry, not plus, minus, okay, of this equation, this relationship. So again, you can leave it like this. Okay, there is no reason to really multiply it all the way out because it's not going to help you solve the problem. It's not going to let you observe where the asymptotes are. All right. One last example here, and I will let you guys go. We're going to do these other examples kind of for homework and for an IP practice, so you can always get practice and talk about them in class. I have x plus 1, x minus 3, okay, in the denominator over here, and then x squared minus 6x plus 9, which if you factor it, I'll go ahead and just do it real quick. It's x minus 3 times x minus 3. Okay, so obviously when I'm talking about LCM, I'm going to talk about this idea of x minus 3 squared. Because this one has 2 factors of it, this one only has 1. It's pretty clear which one has the greater number of factors. That means I'm looking for a denominator like this. If I already have a denominator of x minus 3 in this statement, oops, it's x plus 1 up here, not x, not 2. Okay. All I need to do is multiply 3 by x minus 3, right? And then I'll have my numerator to go with it. X plus 1 and x minus 3 multiply together for x plus 1 and x minus 3, of course. And then if you want to, you can turn this into your least common denominator. And that's my answer there. Okay. Hopefully you guys didn't get too knocked around by the math involved here. There is a lot of moving pieces, so if you got lost, it's totally understandable. I'll see you guys in class for some in-class exercises, and we'll talk a bit more about this if you really need some help on it. Bye-bye.